this owl is in its natural environment. The film was shot at night using a very low level of artificial illumination. So low, in fact, that the owl was quite unaware of the lighting. We can see it because we are viewing the scene through an image intensifier. The film that we've just been looking at was shot using a system similar to this. It consists essentially of a lens which forms the image of the distance seen on the input ends of an image intensifier. The intensifier is inside this housing here. Well, we've already dealt with image intensifiers in program 2, so I'm not going to say anything more about this end of the system. In this program, we're going to concentrate on the lens, looking in particular at 4 aspects. We're going to think about the specification required by the lens. We're going to look at how it was designed, how it was manufactured, and finally, how it was tested. This particular system, the so-called Tri-Light system, was actually produced in this country. And we went along to talk to some of the people who were involved in the project, starting first with Dr. Bill Swift, who had responsibility for drawing up the overall specification of the lens.
Well, first, we must be clear exactly what the lens is expected to do, and for that, we need a precise specification. We must try to be accurate, because if we under-specify the lens, it won't perform as well as the customer wants, whereas if we over-specify it, it will undoubtedly cost more than it needs to, and neither of those is a very satisfactory situation. So we can begin by knowing that the customer wants to recognize animals at night. We need to be more precise than that, so we need the actual illumination levels, and we need the reflectivity of the animals and their contrast with the background. Then we need the size of the animals, and how far away they are, and we need to know how many cycles per meter we must be able to distinguish in order to recognize an animal. And that's something that the customer himself may not know, may not be able to tell us. So we may need to go to the local library to do some literature survey to find out, or we may even need to go out into the field and carry out our own experiments to measure it. Then we need the field of view, and we need some less obvious things, such as, for example, the permissible distortion in the image. And we need some things which aren't optical at all, like how heavy the system can be, and of course how much it can cost. Once we've got that straight, we can move on to the lens itself. Let's start with the field of view. If we know the field of view, and we know the photocathode diameter of the image intensifier, then that fixes the focal length of the lens here, according to a simple geometrical relationship which we have here. Knowing the field of view, we can relate the spatial frequency requirements at the object, which we've already spoken about, to the spatial frequency requirements in the photocathode. Now, we know the MTF of the image intensifier tube, and that looks something like this. Falls off quite rapidly to about 30 cycles per millimeter. And that tells us what we need to have in the way of the lens, because that too must have a modulation transfer function which is high between 0 and 30 cycles per millimeter, but what happens above 30 cycles per millimeter is less important. And that, of course, is quite different than a camera lens, where we would like a long tail on the spatial frequency, but we can tolerate relatively low modulations at low spatial frequency. Now, all that is fine at relatively high light level, which in our case means above about moonlight. At low light level, the situation is different. There, we're very short of light, and the incoming light arrives at random and has fluctuations on it. So we have to have a certain amount of light to get those fluctuations below the level where the animal will be indistinguishable from its background. That gives us a constraint on the minimum collecting area of the lens, and therefore on the minimum diameter of the lens. That means we have the diameter, we have the focal length, we have the field of view, and we have the MTF that the lens is expected to have. Designing the lens, of course, is another matter.
So we know the specification that the lens must meet, but before we see how this is actually satisfied in practice, let's just ask ourselves, what's wrong with this Commoner Gardner converging lens? Well, to find out if there's anything wrong with it, we ought to check out some of its properties, and I can do this using this simple optical bench setup. I'll just mount our lens. Now down here is a source of light, and then comes a pinhole, then our lens, and then a screen. And I've set the screen to lens distance such that we should be forming an image of our pinhole on the screen. Well, let's just see what we've got. And we see that instead of having a nice, sharp point image, we've got rather a colored blur. We've got a blue spot at the center, gradually going over to green to yellow to red. So whatever virtues this lens may have, it certainly got the very serious vice of suffering from chromatic aberration. Stuart?
Well, the cause of this problem is fairly easy to diagnose. It's the dependence of refractive index on wavelength. For the converging lens that Alan used, the short wavelength blue light is refracted more than the long wavelength red light. The white light is dispersed into its coloured components. Blue is focused closer to the lens than red, and this explains the coloured fringes which Alan pointed out. So focal length, image position, and magnification all depend on colour, and this is very undesirable. Well, what about the dispersion of a diverging lens? Again, blue refracted more than red, but this time away from the optic axis. However, light rays can be reversed, and so the diverging lens can bring together the red and blue rays if the angle between them is correct. So we can combine these converging and diverging lenses to cancel dispersion, but the combination is useless since we've lost the focusing action. Well, Isaac Newton thought that there was no solution to this problem of chromatic aberration, and he therefore abandoned the use of lenses and decided to build a telescope which used a curved mirror instead. However, he was wrong because he made the mistaken assumption that the refractive index of a glass was proportional to its dispersion. But have a look at these two diagrams. The lenses here have the same average refractive index, but they disperse light by different amounts. Or here's a pair which disperse light the same amount, but they have different refractive index. We can represent the range of glasses available to the present-day lens designer by plotting the refractive index against the dispersion, which is a measure of how much the red and blue light are separated. The various points on this graph represent different glasses. And you can see that they range from those with high refractive index but low dispersion down here to lenses here which have a lower refractive index but a higher dispersion. Now, the lens designer can use this whole range of glasses in order to cure chromatic aberration. What he must do is to take a converging lens made from a glass with high refractive index but low dispersion, and combine that with a diverging lens made from a glass with low refractive index but high dispersion. If we put two lenses together like that, then we end up with no dispersion, but the lens still has a converging lens action.
Well, let's just check out what Stuart's been telling us. I'll take out our converging lens, and to it I will add a diverging lens. And the diverging lens is made of a different glass. So we'll put both of them together and remount them like this. Now, of course, the focal length of this pair is going to be somewhat larger because I've added a diverging lens. So I'm going to have to bring my combined lens system forward, and we'll see what we get on our screen. And what we see is that although the chromatic aberration has largely vanished, we're still not getting a nice small point. Even if I move the lens back and forth, it just doesn't go nice and small. If you like, the point spread function of the lens is rather large. Now, you may have discovered something similar to this for yourself. Indeed, you will have if you're up to date with those home experiments. Now, in the home experiment, you admittedly only use a converging lens, but we're getting the same effects with our pair. And you will probably know from the unit that there's one way to reduce this rather large point spread function, and that is to alter the aperture of our lens. So let's do just that. We'll bring down the aperture, and we see that the image improves, the point spread function gets smaller.
Again, I'll use a few ray diagrams to explain how this aberration that Alan has just demonstrated arises. Here's a lens with a small aperture, and all of the rays that pass through that lens would pass through a small point on the optic axis if we ignored the diffraction. Now, if we make the aperture somewhat larger, then the rays passing through the edge of the aperture will intersect the optic axis slightly closer to the lens than those passing through the center. And if we make the aperture larger still, then the discrepancy becomes much more pronounced. Now, wherever we put a screen behind that lens, we wouldn't get a sharp image point. The point spread function is rather broad, as Alan just demonstrated. Now, the reason for this problem is that the rays are intersecting the lens surfaces at rather large angles. And when this happens, the simple lens equation breaks down. Well, one way of getting over that problem would be just to use small apertures. But that's not a very suitable solution in the case of the Trilite objective lens, because there we specifically need a large aperture to collect sufficient light. And in any case, small apertures aren't the solution if we have large object fields, because points away from the optic axis will produce rays inclined at large angles to the lens, and again we get aberrations produced. Well, the other solution to this problem is to use more lenses. And that's the solution that Petzval adopted when he designed this portrait camera lens more than 100 years ago. If I put my hand behind this lens, approximately where the plate of the camera would be, you can see that it's focusing a studio light to a fairly small spot. Now, this lens is in fact made up of 4 individual lenses. They're arranged as 2 achromatic doublets, and you can see that the deviation of the light is split between the 2 pairs of lenses. Now, the point spread function of the Petzval lens is in fact much narrower than any of the individual component lenses, and it will therefore produce a much better image. So that's an important point to note. By combining a number of lenses, we can produce a much better system than any of the individual components. That's what the lens designer has to do, to select a certain combination for a certain job, which will minimize the aberrations and optimize the transfer function. So let's have a talk to Phil Rogers at Pilkington's, who actually designed the lens for the Trilite system.
Well, first of all, let me show you the actual lens we evolved, and then I'll describe the process by which lenses are designed. There are 2 things to notice about this diagram. Firstly, that in fact we've used 2 lens groups, as in the Petzval lens that Stuart showed earlier. The second thing is that we've used more lens surfaces in the front group to split up the ray deviations, and we've also used a field flattening lens at the back to give us a flat image surface. Okay, assume I produce this lens as my first trial. What I want to know, obviously, is what sort of quality of imagery it gives, and for this I'd use a computer. Well, first of all, let me demystify the computer before I try using it. Quite simply, it traces a lot of rays from an object point through the lens using the law of refraction, and analyzes what happens to them when they hit the image surface. Okay, I've already input the lens data, so let me try tracing a few rays through it. Well, you can see that the rays are being traced parallel to each other as they enter the lens. This is because we're assuming the object, in fact, is very distant from the lens. Quite obviously, though, there's insufficient scale at this image point here to give us any real idea of what the system's doing. So I'll get the computer to blow up the scale by about 2,000 times. This spot diagram is the result of a large number of rays being traced from one object point through the lens and then intersecting the image surface. We've arranged it so that each ray point here represents 1 unit of light, and therefore the whole spot diagram represents the point spread function of the lens at that image point. If we were to do a Fourier transform of this point spread function, we'd in fact get the modulation transfer function, or MTF, of the system at that point. Okay, now I've got an idea of the quality of imagery given by the lens. I can now use a computer to in fact improve this imagery. I can vary system parameters like, for example, shapes, spacings, refractive indices, etc. I have to constrain the machine to keep within a certain size, maybe. I have to achieve a certain focal length. And I'm trying to optimize point spread functions at all parts of the image field. The limitation of the computer, in fact, is that it can't choose the very best solution straight away. It merely gives you the optimum version of the actual lens design configuration you input. The designer, therefore, has to guide the machine into the correct solution area. And he goes on until, in fact, he gets the optimum version of what he regards as the best possible way of doing that lens. Lens design, therefore, is a sort of an iterative process between designer and machine. The designer pushing the machine all the time until it gets into the best possible solution area, or at least what the designer thinks is the best solution area. Well, OK, I can go back and do a Fourier transform of the point spread function I showed before to obtain the modulation transfer function. And there, in fact, you can see the MTF curve. When I actually specify the manufacturing parameters of this lens system, in fact, I tolerance all the parameters such that the actual manufactured lens would be within a certain percentage of this MTF curve.
Right, we've now reached the stage where the design has been completed. We would then go on to produce a prototype and test that, and after that, the lens would go into full-scale production. Well, Dr. Swift is going to give us a lightning tour of the optical works. Bill, where do we start?
With the glass coming into the factory, moulded roughly to size and shape like this. First, it's ground more accurately to size and shape using diamond impregnated tools like that. And then we stick pitch on the back in this fashion so that you can go onto the runner of a polishing machine like this. The glass goes through several stages of smoothing and polishing. The operation is the same, but the abrasive used is initially coarse and later finer. The curious motion is to prevent the formation of regular pathways and hence marks on the surface, and it leads to spherical surfaces. Aspherics, that is, surfaces which depart from a spherical shape, are more difficult and expensive to make. And this is one reason that Phil tends to conceive his designs in terms of spherical surfaces. Once the surface is smooth, the operator can check the shape from time to time by means of a test plate, which is a precisely made negative of the surface required. The Newton's rings you can see are an indication of the shape of the surface. A perfect match would show no rings, but usually it's sufficient to get down to a few approximately circular rings. When both surfaces of the element have been polished and the thickness is correct, it has to be centered and edged so that the mechanical and optical axes are coincident. We can do that by putting it onto a chuck like this and rotating it, and looking at the reflection of a red cross in the surfaces. As long as it rotates about, then it's not correctly centered. When it's stationary, then it is centered. Then it has the edge ground true to this axis. All the free surfaces are coated in a vacuum evaporation plant to reduce reflections. The doublets are cemented together, and finally all the elements and the housing parts come together for assembly into a complete lens.
One way of testing the assembled lens is to measure the point spread function, and that's essentially what we did earlier in the program with the simpler lenses. But the tri-light lens is specified in terms of MTFs, and so it's obviously far more convenient if we measure the MTF directly. And in fact, that's what this piece of equipment here is designed to do. Well, let me first of all give you a general guided tour of the equipment. This box here contains the incoherent source of light and the object gratings. Light from here is reflected from this small mirror out to the large parabolic collimating mirror in the distance, and then back to the lens under test. And we have, in fact, got a tri-light lens mounted in the test jig. Behind the lens is a photomultiplier for measuring the intensity in the image, and that's connected up to this rack of electronics, which calculates the MTF. That, in turn, is connected to a recorder, which plots out the MTF on a graph. And as you can see, the important components of this instrument are mounted on a large 5-ton granite block, and that's to preserve the stability and isolate the system from vibrations. Well, that's the general layout of the system. Let me now go into a little bit more detail about how the object is produced. This little model here represents the object. You can see that there's a square wave grating here behind a narrow slit. And if I, in fact, change the orientation of this grating with respect to the slit, the spatial frequency measured along the slit changes. I can go all the way from 0 spatial frequency here, right up to the spatial frequency of the grating. So, in fact, I only need one grating to produce a continuous range of spatial frequencies. Now, the tri-light lens will form an image of this object behind it. And we can analyze the modulation in the image by putting a slit in front of the photomultiplier and scanning the slit across the image. And obviously, if we consider that this was the image now, the photomultiplier will give 0 output, it'll go to a maximum, it'll go back to 0, and it'll oscillate periodically as we scan across the image. That means that we convert the spatial information in the image into a temporal frequency. The voltage out from the photomultiplier oscillates in time. And that's a characteristic of many scanning systems. Now, many of you may have been worried by the fact that this grating here is, in fact, a square wave grating and therefore contains many higher harmonics, whereas the MTF is the response for a single spatial frequency. Now, we can get over that problem by, in fact, removing all the higher harmonics from the photomultiplier output by electronic filtering. That will just leave us with a single spatial frequency, and the modulation at that spatial frequency will tell us the MTF. Now, I can actually get the machine to measure the MTF quite simply by depressing this switch here. And you can see that what's happening is that the pen is sweeping across in spatial frequency in this direction. The MTF plotted vertically is falling away. As we hope for with this design, the MTF is high in the range of low spatial frequencies. Now, in fact, if we were to compare this graph with the computer prediction that we showed you earlier, we would find that the two agreed very well to within 5% or so. And that's an indication of how well the people in the workshop and in the assembly room have done their job.
And so we arrive at the tested lens system. To sum up the key points then, the first thing to note is that the lens specification must be drawn up knowing the use to which the lens is to be put. Then on the design side, the designer must bear in mind manufacturing and indeed commercial restraints. And finally, of course, the lens must be tested to be sure that it meets the specification. Now, we've only been concentrating on one particular lens system, but very much the same considerations apply to designing any practical lens system.